Dear students, today I am going to explain semiconductors. ఎవరైనా ఛానల్ సబ్స్క్రైబ్ చేయకుంటే చేయండి. Matter exists in three different forms. Solids, liquids and gases. On the basis of arrangement of atoms, solids are of two types. One, crystalline solids, and two, amorphous solids. Solids which are having specific geometrical shape and periodicity in the arrangement of atoms are called crystalline solids. Crystalline solids have definite shape. Amorphous solids have no definite shape. Crystalline solids have fixed melting and boiling points. Melting point and boiling points. No fixed melting point and boiling points. Crystalline solids are anisotropic, means substances which have different properties in different directions are called anisotropic. These are isotropic. Example, sodium chloride, lead sulfide, etc. Powders, no definite shape. Amorphous solids are powders. Energy bands in solids. Consider a silicon crystal of n atoms. Atomic number of silicon is Z of silicon 14, 1s2, 2s2, 2p6, 3s2, 3p2. These are completely filled orbitals. 1s2, 2s2, 2p6. These are valency electrons. Electronic configuration of outermost orbit. Four electrons. In each atom there are 4 electrons, 4 valency electrons. And 4 empty states. The crystal consists of n atoms. In crystal total valency electrons 4n, empty states 4n. The energy band, this is 1s2, 2s2, 2p6. These are completely filled. This is the energy band consisting of 4n electrons. This is VB valency band. The upper energy band consisting of 4 empty states is called conduction band, and the middle is forbidden energy region. Energy band consisting of valency electrons is called valency band. Conduction band, the upper energy band which should be filled with free electrons. Filled with free electrons is called conduction band. The energy gap between valency band and conduction bands is called forbidden gap. The valency band VB and conduction band forbidden gap. On the basis of conductivity, solids are of three types. Conductors, semiconductors and insulators. Substances which allow electric charges to pass through them are called conduction band, which partially allow electric charges to pass through them are called semiconductors, which do not allow electric charges to pass through them are called insulators. In the energy band diagram of conductors, valency band and conduction bands overlap on each other. In semiconductors, forbidden energy gap is about 1 electron volt. Here Fermi forbidden energy gap is 5 to 10 electron volts. In conductors, electrical conductivity due to free electrons. Here electrons and holes, here only electrons. At 0 Kelvin acts as superconductor, acts as an insulator. At room temperature, acts as conductor. Insulator. But difference ఏమి రాదు. రూమ్ టెంపరేచర్ దగ్గర కూడా acts as an insulator. When temperature increases, resistance increases. Here resistance decreases. Here also resistance decreases. Adding impurities, resistance increases, resistance decreases, no change in resistance. Example, all metals, germanium and silicon, fourth group elements. Wood, plastic, etc. In this energy level diagram, valency band and conduction bands overlap on each other. This is a conduction band. This is valency band. VB, CB overlap on each other and forbidden energy gap is 0. In here valency band, conduction band around 1 electron volt. This is valency band and 5 to 10 electron volts. Here energy gap in germanium is 0.7 electron volts and in silicon this is 1.1 or to 1.2 electron volts. This is conductors, semiconductors and insulators. Semiconductors are of two types. Semiconductors are of two types. One, intrinsic semiconductor. Pure semiconductors are called intrinsic semiconductors. Pure semiconductors are called intrinsic semiconductor. At 0 degree Kelvin, it acts as an insulator due to strong covalent bonds between valency electrons at high temperatures. At high temperatures, due to breakage of covalent bonds, free electrons and holes are created. Hence, at room temperature, at high temperatures, room temperature acts as a conductor. Here, conduction is due to breakage of covalent bonds. Hence, number of free electrons equal to number of holes. That is, n electrons is equal to nh. Both are current carriers. In external electric field, both move in opposite directions. Fermi energy level lies at the middle of forbidden energy region. Conventional current I equal to I electron plus I hole equal to n electrons into E into A into drift velocity of electrons, n holes into E into A into drift velocity of holes. In this, n number of electrons equal to number of holes. Hence, NEA into drift velocity of electrons plus drift velocity of holes. Current density J equal to I by A equal to NE of VDE plus VDH. Conductivity sigma equal to J by intensity of electric field NE into VDE by E plus VDH by E. This equal to NE into mobility of electrons plus mobility of holes. Current density J equal to, where mu E mobility of electrons and mu H mobility of holes. Pure semiconductors are called intrinsic semiconductors. Example, germanium. మరి ఇలా మొత్తము జెర్మేనియం యాటమ్స్ తీసుకున్నట్లయితే మరి ఒక ఎలక్ట్రాన్ను టెంపరేచర్ పెరిగినప్పుడు అట్ రూమ్ టెంపరేచర్స్ డ్యూ టు ద బ్రేకేజ్ ఆఫ్ కోవలెంట్ బాండ్స్ electrons and holes are created. This is free electron and this is hole. Here number of electrons equal to number of holes. Both are the current carriers. Fermi energy level lies nearer to Fermi energy level. It is the average energy of electrons in conduction band and holes in valency band. Fermi energy level. Average energy of free electrons in conduction band and holes in valency band. In external electric field, these electrons and holes move in opposite direction. Electrons move towards positive terminal and holes move towards negative terminal. These are free electrons and these are holes. Impure semiconductors. Impure semiconductors are called extrinsic semiconductors. These are of two types: N-type semiconductor and P-type semiconductor. Germanium is a tetravalent element. Arsenic is a pentavalent impurity. ఇటు చుట్టూ జెర్మేనియమ్స్ ఉన్నాయి. ఇది ఆర్సెనిక్. Arsenic is a pentavalent impurity. Out of 5 electrons, 4 electrons are covalent bonded with 4 neighboring germanium atoms. The remaining electron is a free electron. Due to thermal agitation, due to breakage of covalent bonds, free electrons and holes are created. Hence, in this, electrons are the majority carriers and holes are the minority carriers. In this, electrical conduction is mainly due to negatively charged particles called electrons. Hence it is called N-type semiconductor, negative type of semiconductor. N-type semiconductor is due to the addition of pentavalent impurity like arsenic, antimony and phosphorus, etc. Here arsenic donates one free electron to the neighboring germanium atoms. Hence arsenic is a donor impurity. Donor impurity. In this, electrons are the majority carriers. And holes are minority carriers. N electrons is greater than N holes. Fermi energy level lies nearer to conduction band. Electric current is due to free electrons. It is electrically neutral. In this, Ni square, N intrinsic square equal to Ne into N holes. Number of electron concentration into hole concentration equal to Ni square. This is about N-type semiconductor. In P-type semiconductor is due to the addition of trivalent impurity. Like indium, gallium, aluminium, etc. Indium is a trivalent impurity. Arsenic is a tetravalent. Germanium or silicon is a tetravalent element. Germanium requires 4 electrons to complete the covalent bonds. But arsenic is a indium is a trivalent impurity. Germanium requires 4 electrons to complete the covalent bonds. This electron deficiency in indium behaves like a positively charged hole. Due to the thermal agitation, breakage of covalent bonds, free electrons and holes are created. In this, holes are the majority carriers, electrons are the minority carriers. Conventional current is mainly due to positively charged carriers, holes. Hence it is called P-type semiconductor or positive type of semiconductor. Here arsenic indium accepts one more electron from neighboring germanium atoms. Hence indium is an acceptor impurity. In this, number of holes is greater than number of electrons. Fermi energy level lies nearer to valency band. Here holes are the current carriers, and this N-type P-type semiconductor is also electrically neutral. It is an acceptor impurity. Acceptor impurity. Here holes are the majority carriers. and electrons are minority carriers. N holes is greater than N electrons. Fermi energy level lies nearer to valency band. Electric current is due to the movement of holes. It is electrically neutral and Ni square equal to Ne into Nh. ఇది 2 కేసెస్లో సేమ్. Ni intrinsic electron concentration in intrinsic semiconductor. Of electrons in intrinsic semiconductor. Ne electron concentration Nh hole concentration. Both N-type and P-type semiconductors are electrically neutral. PN junction, a device with 2 electrodes, is called a junction diode. A device with 2 electrodes is called PN junction diode or junction diode. A trivalent impurity is added from one side and pentavalent impurity is added from another side to a germanium or silicon crystal. A junction is formed is called PN junction. In P region, holes are the majority carriers. And electrons are minority carriers and vice versa. మా N రీజియన్లో దీనికి రివర్స్లో తీసుకుంటాం అంతే. అంటే హియర్ N హోల్స్ ఈజ్ గ్రేటర్ దెన్ N ఎలక్ట్రాన్స్ అన్నమాట. సెకండ్ వన్, ఎలక్ట్రాన్స్ ఇన్ N region crosses over the junction to P region and holes in P region crosses over the junction to N region. This process is called diffusion. Electrons in N region and holes in P region crosses over the junction is called diffusion. Due to that, near the junction, a region is formed due to immobile ions near the junction. A region is formed due to immobile ions called depletion layer. Electrons in N region crosses over the junction to P region, leaving vacancy in N region. And electron entering the P region becomes negatively charged. Near the junction, a region is formed due to immobile ions. This is called depletion layer. Due to these immobile ions causes an opposition to further movement of electrons and holes. It is called potential barrier. Electric field in potential difference between the ends of depletion layer is called barrier potential. It is 0.3 volt for germanium, 0.7 volt for silicon. Germanium and silicon. Energy gap equal to 0.3 electron volt in germanium, 0.7 electron volt in silicon. Electric field is directed from N to P region. Electric field intensity of electric field E equal to V by D. V barrier potential and D width of depletion layer. Wavelength of light or photon needed to transfer an electron from valency band to conduction band. Wavelength lambda equal to 12,400 by energy gap in electron volts యాంగ్స్ట్రామ్స్ అవుతుంది. మరి ఈ ఫార్ములా తోటి వేవ్ లెంగ్త్ ఆఫ్ లైట్ నీడెడ్ కనుక్కోవచ్చు. హియర్ ఎలక్ట్రిక్ ఫీల్డ్ ఈజ్ డైరెక్టెడ్ ఫ్రమ్ ఎన్ రీజియన్ టు పి రీజియన్. ఫార్వర్డ్ బయాస్. P region is connected to P region is connected to positive terminal of the battery and N region is connected to negative terminal of the battery. This type of connection is called forward bias. P region is connected to P region is connected to positive terminal and N region is connected to negative terminal. This type of connection is called forward bias. Potential at P side is comparatively greater than potential of N side. This is 5 volt and 0 volt like this. Due to repulsion between like charges, holes in P region and positive terminal, electrons in N region and negative terminal, both electrons and holes move towards the junction and width of the depletion layer decreases. Width of depletion layer decreases, barrier potential decreases, resistance of junction decreases and offers more current to flow across the junction due to diffusion of majority carriers. Forward current I equal to V difference VB by R plus R forward. In ideal diode, R forward equal to 0. Therefore, I equal to V difference VB by R plus RS. Reverse bias. P region is connected to negative terminal of the battery and N region is connected to positive terminal. This type of connection is called reverse bias. P region to negative terminal, N region to positive terminal. This type of connection is called for reverse bias. Potential of N side is greater than potential of P side. This is in reverse bias. Due to the attraction between unlike charges, both holes and electrons move towards the battery. Width of the depletion layer increases, barrier potential increases, resistance of junction increases, and no current flows across the junction due to majority carriers. Width of depletion layer increases, barrier potential increases, resistance of junction increases, and no current due to majority carriers. Due to drift of minority carriers, small current flows across the junction called reverse bias current. Reverse resistance of ideal diode equal to 0. Reverse current is almost negligible. Reverse current I reverse equal to V plus VB by R plus R reverse. In ideal diode, R reverse equal to infinity. Therefore, I reverse is almost equal to 0. This is barrier we applied. This is forward bias. Forward bias. V difference VB. This is reverse bias. V plus VB. And this is unbiased. Unbiased. Forward bias, reverse bias, and unbiased. Rectification. Reverse bias lo, as reverse bias voltage increases, Reverse bias current first increases very slowly and then rapidly. This is applied voltage. V forward, V reverse. This is current I. This is in reverse bias, pike forward. The process of converting alternating current into direct current is called rectification. The device used to convert alternating current into direct current is called rectifier. Rectifiers are of two types: half wave rectifier and full wave rectifier. This is half wave rectifier circuit. Step down transformer 230 to 6 volts, and this is a PN junction diode, P and N region. This is load resistance RL. In full wave rectifier, this is one diode D1 and this is another diode D2. This is load resistance RL. This diode D1, D2, A, B and center tapped at C. In half wave rectifier, single diode is used. Single diode is used in half wave rectifier. Two diodes are used in full wave rectifier. Ordinary step down transformer is used. Here center tapped transformer. Function of center tapped transformer is, with respect to C, A is taken as positive, B acts as negative and A is taken as negative, B acts as positive with respect to earth, that is center tapped. In half wave rectifier, only positive half cycles are converted into pulsating DC. Only positive half cycles are converted into pulsating DC. This is input and this is output. In half full wave rectifier, both the half cycles are converted into pulsating DC. This is a positive half cycle. During positive half cycle, the diode is in forward bias. Current passes through diode and load resistance. During negative half cycle, diode is in reverse bias. And in next positive half cycle, diode is in forward bias. And during negative half cycle, diode is in reverse bias. Here only positive half cycles are converted into pulsating DC. In this, both the half cycles are converted into pulsating DC. Output frequency equal to input frequency. Here output frequency equal to 2 into input frequency. అంటే ఇక్కడ ఒక వేవ్కి ఒక పల్స్ ఉంటుంది కాబట్టి n వేవ్స్కి n పల్సెస్ ఉంటాయి. ఇక్కడ ఇంతవరకు ఒక వేవ్కి 2 పల్సెస్ వచ్చాయి కాబట్టి అవుట్పుట్ ఫ్రీక్వెన్సీ ఈక్వల్ టు 2 into ఇన్పుట్ ఫ్రీక్వెన్సీ. Efficiency n equal to output power by DC output power by AC input power. Same formula here also, n equal to P output by P input into 100%. into 100%. Efficiency n equal to 0.406 into RL by RF plus RL. Here efficiency equal to 0.812 by into RL by RF plus RL. R load resistance RF. In ideal diode, R forward equal to 0. Therefore efficiency n equal to 40.6% in half wave rectifier and 81.2% in full wave rectifier. Output frequency of full wave rectifier is double that of input half wave rectifier. Eta full wave rectifier equal to 2 into eta half wave rectifier అవుతుంది. Efficiency in full wave rectifier is 2 times more than 2 times or double that of in full wave half wave rectifier. That is input waveform. This is output waveform. Output. This is D1, D2. This is D1, D2. But D1 అన్ని పాజిటివ్లు వస్తాయి. Both the half cycles are converted into pulsating DC in full wave rectifier. Only positive half cycles are converted into pulsating DC in half wave rectifier. Efficiency of half wave rectifier is 40.6% and that of full wave rectifier is 81.2%. మా బ్రిడ్జ్ రెక్టిఫైర్ అని ఇంకా ఉంటుంది, దాంట్లో 90% వరకు ఉంటుంది. ఇంకా వీటిని ఫిల్టర్ సర్క్యూట్స్ నుంచి పంపినట్లయితే వీటిని స్మూతన్ చేయొచ్చు అన్నమాట. అప్పుడు మనకు డీసీ వస్తుంది. అంటే ఆల్టర్నేటింగ్ కరెంట్, డైరెక్ట్ కరెంట్ మీకు తెలుసు. ఆల్టర్నేటింగ్ కరెంట్ హూజ్ డైరెక్షన్ reverses in equal intervals of time is called alternating current. The current whose direction remains same is called direct current. టార్చ్ లైట్ బ్యాటరీల్లో వచ్చేటువంటిది డైరెక్ట్ కరెంటు, మన ఇళ్ళల్లో వచ్చేటువంటిది ఆల్టర్నేటింగ్ కరెంట్ ఏసీ. దిస్ ఈజ్ అబౌట్ సెమీకండక్టర్స్, Zener diode and logic gates already given in previous videos. షేర్ ఎవరైనా లైక్ చేయకుంటే అంటే సబ్స్క్రైబ్ చేయకుంటే సబ్స్క్రైబ్ చేయండి ఛానల్, లైక్ చేయండి, షేర్ చేయండి. ఏమన్నా డౌట్స్ ఉంటే కామెంట్స్లో చెప్పండి. థ్యాంక్ యూ.